Welcome back to the deep dive.
Put it.
We are plunging headfirst into unsupervised learning, really the art of finding meaningful structure in just raw, unlabeled data.
That's right. And our mission today really is to synthesize the three core techniques you need to understand. Principal component analysis, or PCA, for sort of wrangling dimensions.
Right.
And then two major clustering techniques, K-means and Gaussian Mixture Models, GMM.
Okay.
By the end of this deep dive, you should have a pretty thorough conceptual grasp of how, chaos turns into actual insight.
Sounds good.
Yeah.
I think the best place to start is probably with the problem these techniques were invented to solve in the first place.
Mm-hmm.
The curse of dimensionality. It sounds dramatic, but why are data sets with lots of features, these high dimensions, why are they so tricky to manage?
It really is a curse, a term coined by mathematician Richard Bellman way back. Think of it conceptually, right? If you live on a single line, one dimension, finding your neighbor is easy.
Sure.
Move to a flat plane, two dimensions, the space expands, but it's, still manageable. But as you jump to 50, 100, maybe 1,000 dimensions, the volume of that space just explodes, combinationally.
A combinatorial explosion. Wow. I'm picturing trying to find like one specific grain of sand across 1,000 different beaches all at once.
That's exactly the kind of scale issue we're talking about. The data points, even if you have millions of them, they become incredibly sparse relative to the sheer size of the space they're in.
Sparse. This is spread out.
Yeah, very spread out. And this sparsity makes visualization basically impossible, and it causes algorithms to, break down or become computationally infeasible.
Right.
They just struggle to find statistically significant patterns because everything is so far apart from everything else.
So the fundamental goal of unsupervised learning isn't just finding patterns, but maybe first, escaping that curse, finding a simpler way to look at the data.
Precisely.
We need the best possible simplification, whatever that means.
Exactly. And best here means a representation that's maybe lower dimensional or perhaps highlights independent features. Anything that cuts down the complexity while keeping as much of the original information as possible.
Okay.
And that brings us straight to dimensionality reduction and specifically PCA.
PCA, principal component analysis.
Right.
The ultimate tool for reorganizing this high-dimensional data. What's the sort of the core ambition of PCA?
The core ambition is actually pretty simple. Identify the directions, think of them as new axes along which the data varies the most. It's like, imagine throwing a cloud of data points into the air. PCA tries to find the angle from which they look most stretched out.
Right, that angle where they seem longest.
That angle captures the most information, the most variance.
I like that idea, finding the axis of maximum stretch. It means we're not just, arbitrarily cutting features out.
No, not at all.
If we have 100 features, PCA isn't just picking the 10 most obvious ones. It's creating maybe 10 new super features that are combinations of the original 100. Is that right?
That's the key insight, yes. We're building a new orthogonal basis axes that are perpendicular to each other, where the first axis, the first principal component, or $1, captures the biggest chunk of that spread, that variance.
Okay, let's focus on $1. If it has to capture the largest variance, how is it actually constructed? It's a linear combination of all the original features, isn't it?
Correct. $1 is essentially a weighted average of all your original features. The weights themselves, those are called the loadings.
Loadings, okay.
Yeah, imagine $1 is like a final score, and the loadings tell you how much weight each of the original variables contributes to that score.
So if a loading is near 0,
then that original feature doesn't contribute much to the variance that $1 is capturing. It's not important for that specific dimension of variance.
that helps clarify the jargon. Loadings are influence scores.
Yeah.
Got it. Now, our sources mention a crucial constraint on these loadings. Why do we need that?
Yes. We need to normalize them. Basically, the sum of the squares of the loadings has to equal 1.
Why, though?
Well, if we didn't have that constraint, we could just multiply the weight of every feature by, say, 1,000,000. And the variance would become arbitrarily huge, which kind of defeats the purpose of finding the inherent structure.
Right, you'd just be inflating it.
Exactly. The constraint ensures we're finding the direction of maximum variance, not just making the measurement bigger artificially. It keeps the scale consistent.
That makes perfect sense. So PCA finds this optimal direction using the best set of loadings. What happens next? What do we do with that direction?
So every data point you have is then projected onto this new direction, the one defined by that loading vector.
Projected, like casting a shadow.
Kind of, yeah. The resulting projected values, those are what we call the principal component scores. These scores are the actual coordinates of your data in that new condensed dimension defined by z-r's.
Okay, and once we have z-1 capturing the maximum spread, we move on to z-2, the second principal component.
Right.
And this is where that orthogonality rule comes in, which sounds important for efficiency.
Absolutely critical. Z2 also wants to maximize variance, but it has one strict rule. It must be completely uncorrelated with z-dollars.
Uncorrelated. So orthogonal.
Yeah.
Perpendicular.
Mathematically speaking, yes, orthogonal. It's looking for the next best direction of variance that tells you something new, something that z$n didn't already cover.
So if we were looking at, say, customer data, z$n might capture something like overall spending level.
Quite plausible, yeah.
Then z$n might capture something totally uncorrelated, like maybe regional purchase habits, without repeating the spending info that's already in z$n.
Precisely that kind of separation.
Yeah.
And this sequential process allows us to quantify exactly how much information we retain with each new component.
Ah, right. That's the proportional variance explained, the PVE.
Exactly. PVE. It's a percentage that tells you, how much of the overall chaos, the total variance, is explained or made sense of by that single component.
And this is the real payoff of PCA, isn't it? Our sources really emphasize that PCA doesn't actually lose variance. It just concentrates it.
It's a phenomenal reorganizer. That's a great way to put it. If you sum up the variance across all your original, say, 100 features, and then you sum up the variance across all the resulting 100 principal components, those two totals are mathematically identical.
Identical.
Identical. PCA simply shoves maybe 80 or 90% of that total variance into the first few components, allowing you to potentially discard the rest, which were mostly contributing noise anyway.
That's the magic then. The total information is preserved, just shifted into a much more accessible, smaller format.
It allows you to transform a complex, say, 100-dimensional cloud into maybe a simple 3-dimensional scatter plot you can actually look at, potentially without sacrificing the critical insights.
Okay, that's powerful. So we've used PCA, we've reduced the noise, simplified the dimensions. Now let's shift gears to the next stage, finding inherent groups within that cleaner data.
Right, clustering.
Clustering.
Clustering is really the quest for homogeneous subgroups. We want the data items within a cluster to be highly similar to one another and highly dissimilar to items in other clusters.
And we see clustering applications everywhere.
Right.
Not just analyzing customer segments for marketing.
Oh, yeah, all over.
But even internally, maybe clustering input variables based on how correlated they are, just to remove redundant predictors before you even start modeling.
That's a very common pre-processing step, yes. It simplifies the model building.
So the workhorse technique here seems to be k-means clustering.
Definitely the most well-known.
It's simple, fast, driven by a clear objective. But the first thing is, the user has to pre-specify the number of clusters k.
That's right. You have to tell it how many groups you're looking for up front. That can be a challenge sometimes.
Right, choosing k.
Yeah.
But once you've chosen k, the algorithm does this, well, it seems like a deceptively simple 4-step dance. Can you walk us through those steps again?
Sure. It starts by randomly picking k data points to act as the initial centers or centroids for your clusters.
Okay, random start points. Step 1.
Step 2. Every other data point gets assigned to whichever centroid is closest to it, usually based on Euclidean distance.
Makes sense. Assign to the nearest center. Step 2.
Step 3. The algorithm recalculates the position of the centroid for each cluster. It does this by taking the mean, the average position, of all the points currently assigned to that cluster.
So the center moves to the middle of its assigned points. Step 3.
Exactly. And finally, step 4. Repeat steps 2 and 3. Keep assigning points, keep recalculating centroids. Until the assignments stop changing. Until no point wants to switch clusters after the centroids are updated. That's convergence.
It's incredibly intuitive. You just keep shuffling points until things settle down. That simplicity must be its biggest strength.
It is. K-means is easy to explain, easy to implement, and surprisingly efficient. Its computational complexity is roughly linear with the number of data points, which means it scales really well to massive data sets. That's crucial today.
But there's always a but.
Always.
Where it gains in simplicity, it seems to lose some nuance. I know it struggles when the clusters aren't these nice, neat, perfectly round blobs.
Yeah.
What are its main weaknesses, conceptually?
Yeah, the biggest limitation is probably that it creates hard boundaries. A data point is in cluster A or it is in cluster B. period.
No fuzziness.
No fuzziness. And this makes it extremely sensitive to outliers. A single outlier can drastically pull the mean, the centroid, away from the cluster's natural center.
Ah, because it uses the means.
Exactly. It also struggles when clusters have very different shapes, like one tight ball and one long ellipse, or when they have very different densities. K-means implicitly assumes clusters are roughly spherical and equally dense.
Right, because using the mean to define the center naturally favors those circular shapes. Thinking about that image segmentation example helps illustrate it.
It does. If you cluster the colors in an image using K-means, you define K principal colors. Every single pixel in that image is then forced to take on the exact color of its assigned cluster centroid.
Right.
It works, it segments the image, but it creates these sharp, sometimes artificial-looking boundaries where the different color clusters meet.
That's a great visual for that hard boundary problem. And, well, this weakness leads us pretty naturally to our final technique today, which tackles that very issue. Gaussian Mixture Models. GMMs.
Right.
This is where we get into probabilistic clustering.
GMNs take a fundamentally different route. Instead of assuming a cluster is defined by a single point, its mean. GMM assumes that the data was actually generated by a mixture of several probability distributions, specifically Gaussian or normal distributions, those familiar bell curves.
Okay, so instead of forcing a point into one cluster or another, we're thinking about the clusters themselves, probabilistically, based on where these hidden bell curves overlap.
That's the core idea. The probability distribution of the entire dataset, expound, is modeled as a weighted sum of individual Gaussian components.
Right.
Each component has its own mean, its own covariance matrix, which defines its shape and orientation.
So it doesn't have to be spherical.
Exactly. It can be oval, diagonal, whatever the covariance matrix dictates. And each component also has its own mixture weight, saying how prominent that component is in the overall mix.
This sounds much more flexible than K-means, especially for real-world data where boundaries are often messy.
It is much more flexible.
So how does the model figure out the parameters, the means, the covariances, the weights for these underlying Gaussian distributions? It sounds complex.
It is, and it can't be solved directly analytically. So we use an iterative approach called the expectation maximization algorithm, or EM. It's a really clever two-step process that cycles back and forth.
Let's try to break down those EM steps conceptually, maybe without getting lost in the math.
Okay, we start with the E step, the expectation step. This is where, for every single data point, we calculate the probability that it belongs to each of the K components.
Ah, so not just assign it to one.
No, this gives us what are called responsibilities. It's a soft assignment. It might tell you, okay, this data point has a 70% chance of belonging to component A, a 25% chance of belonging to component B, and a 5% chance of belonging to component C.
So the E step gives us probabilities, a measure of belief or uncertainty about where each point fits?
Precisely. That's the conceptual power over K-means. It handles ambiguity. It tells you how confident it is about the assignment.
Okay, that's the E step. What about the M step?
Then we move to the M step, the maximization step. This is where we use those soft assignments, those responsibilities we just calculated.
The 70%, 25%, 5%.
Yes, we use those probabilities as weights to update all the parameters, the means, the covariances, and the mixture weights for all K components.
So we use those probabilistic beliefs to refine our definition of each underlying Gaussian distribution.
That's it. The E step computes the soft assignments based on the current parameters, and the M step updates the parameters using those soft assignments. It iterates back and forth, E then M, E then M.
Similar to K-means iterating, but conceptually very different.
Very different. It keeps adjusting the statistical definition of each cluster until the model finds the parameters that maximize the overall likelihood of observing the actual data you fed it.
That conceptual difference is really key. K-means finds groups using hard physical distance. GMM finds groups using statistical probability and handles uncertainty, handles overlap much more gracefully.
Absolutely. If you suspect your clusters overlap or have non-spherical shapes, GMM is generally going to be a much better, more realistic choice. It doesn't force those artificial hard boundaries.
Okay, so if we step back now and try to synthesize all this, we have these two broad approaches we discussed. PCA for dimensionality reduction and clustering techniques like K-means and GMM for finding groups. Beyond the obvious difference, how do they fundamentally differ in their main purpose?
Well, PCA is primarily focused on the the columns of your data matrix, if you will.
Right, the variables.
Its goal is to create a more efficient, lower dimensional representation of your variables. Clustering, on the other hand, focuses on the observations, the rows of your data matrix.
The individual data points are samples.
Exactly. Its goal is to find homogeneous subgroups among those observations. They're solving different kinds of simplification or efficiency problems operating on different axes of the data.
But they often work hand in hand, right? It's not usually in either situation.
Oh, absolutely. Very often used together. You can think of PCA as an essential pre-processing step.
Cleaning the data first.
Yeah, by using PCA to reduce noise, get rid of less important dimensions, and really concentrate the information, you can then feed a much cleaner, lower dimensional data set into your clustering algorithm, whether that's k-means or GMM.
And that presumably improves the clustering result.
It often improves performance dramatically, yeah. Makes the clusters potentially clearer, makes the algorithm run faster. It's a common workflow in pattern recognition, classification, anomaly detection, you name it.
This has been a really fantastic deep dive into finding order in the digital wilderness, as it were.
Yeah.
We started with that slightly terrifying curse of dimensionality.
It was daunting.
And we built up the toolkit PCA, k-means, GMM, to actually tame it.
And if there's one sort of powerful idea to really take away from all this, I think it's how variance is treated, especially by PCA.
That core insight that PCA doesn't lose the variance, it just rearranges it, reorganizes it.
Precisely. The total information content measured by variance of your original complex data set, it's entirely captured by variances of the principal components. By focusing on just the first few components that explain most of that variance, you're not really sacrificing information. You're simply choosing a simpler, more informative lens to view your data through.
Think about that for a moment. Maybe in the context of any complex decision you, the listener, have to make today, maybe in business or health or finance, you feel like you're drowning in variables.
We often are.
What if you could isolate the minimal set of truly independent, uncorrelated factors that still explain, say, 90% or 95% of the outcome you care about? That's the real analytical power here, moving you from that overwhelming complexity to the core insight.
That's the power of PCA.
That's the challenge for you to perhaps explore this week. Find those principal components in a problem you face.
Excellent thought. We'll see you next time for another deep dive.